So I'm Dieter from the Definity Foundation, and I would like to welcome everybody to today's community conversation on threshold ECDSA system integration. So the community conversation series is a platform for you to hear about ongoing projects from contributors to the IC ecosystem, and it also gives you the opportunity to ask questions. As many of you know, the foundation has been working on the implementation of a novel threshold ECDSA scheme for the internet computer for some time now. And last year, our principal researcher, Victor Schub, has given a community conversation about threshold ECDSA signing last year. So he was introducing the mathematical foundation of threshold ECDSA signatures to the community. And in today's community conversation, Andrea Cerulli and myself will be giving you some insights into the so far much less discussed and lesser known aspects of this threshold ECDSA implementation, namely the threshold ECDSA system integration. And this system integration is essentially dealing with stuff like key generation, deployment, and rollout. So key generation, how do the subnets get the threshold ECDSA key, then the deployment, how many threshold ECDSA keys will the IC have? How often will each key be replicated? How many subnets will support ECDSA? So all those have been questions that are not totally straightforward that we needed to address in addition to the core protocol implementation. And it was actually much more effort than we thought. And we thought it's a good idea to share some learnings and share the overall ideas of this with you. And finally, the rollout. So how to roll out the ECDSA feature on mainnet. And if we go to the next slide, we can look at the deployment architecture. So we are seeing here one subnet. As we all know, the subnet is built up from many replicas as a foundation that provide compute and storage functionality. And now in an ECDSA-enabled subnet, the nodes will hold a threshold shared ECDSA key. So this green-blue key here. And this key is secret shared among the nodes of the subnet, meaning that nobody holds the full key, but everybody holds a key share, but the one key share of its own has no information about the key. Only a quorum of the nodes can use the key to create signatures with the key. And now security-wise, what we did is we decided that on subnets that are enabled with ECDSA, we do not want to have user canisters on, because user canisters always provide, even if the execution is isolated, some more risk in terms of sandbox escape attacks and things like this. So we said we don't want to have user canisters for this reason on the subnets. And overall, we want to have the similar level of security as on the NNS subnet. So it means a large subnet, 34 plus nodes, so 34 in the beginning, then growing as the NNS grows. Also similar in terms of decentralization, so selection of nodes from different node providers and geographic distribution and data centers, like for the NNS, so similar, and also the node provisioning being done in a similarly or more secure way than for the NNS. So if we go on, we will have any other subnets which are not ECDSA enabled. So those subnets, they have user canisters on them, and those canisters now can make use of the ECDSA functionality. So a canister will be able to retrieve its own public key and make use of its own private key for signing operations. And now let's talk a bit about how the key management works. So the ECDSA subnet will only host one ECDSA key, and this one key allows for deriving now for each canister its own private and public key. Let's call it a master or root public key or private key for the canister. And now we can use further BIP32 key derivation so that the canister can derive an unlimited number of keys as if it wishes, for example, for Bitcoin integration. And now a canister can obtain its public key or any of the derived keys, or it can request a signature from the ECDSA subnet for one of its keys. And only, of course, a canister that controls a key may request a signature with it. And now all this communication works cross subnet because all the user canisters are on other subnets, as we said. So we needed to build some new crossnet communication in. And if we go ahead now, we will have the next slide showing a backup subnet. So we want to have multiple instances of this key on the internet computer because we think the unlikely event of the ECDSA subnet getting destroyed should be covered for. So there could be a disaster, whatever way, deterministic error. So it's out. Then we want to have a backup subnet. So what we could do, for example, switch over that the backup subnet now accepts API requests from other app subnets. And meanwhile, we could do a recovery of the broken subnet or set up a new subnet with the key so that we again have 2 copies at least of the key around on the internet computer. So that's a kind of disaster recovery architecture, which we think is really important because we assume that this ECDSA key will secure substantial value, for example, in the context of Bitcoin integration or Ethereum integration, which is coming later. If you go ahead, let's now look at rollout and distributed key generation. So we do this using 3 different NNS proposals. So that's now how the key management comes in. So key generation, key distribution to other subnets, and enabling subnets for signing. So number 1 is generating a fresh ECDSA key. So that's what we are seeing now. So we make a new NNS proposal proposing that the subnet A here on the right should hold a new ECDSA key. Let's call it sec P256K1, key number 1. Actually, this is a simplification of the reference of the identification scheme for keys. In practice, how we implement it is that we have 2 parts for a key identifier. The first part being a variant expressing the curve the key is on or the operations are done on, and the second is an identifier like key 1 here. And now with this key identifier, so when we make this proposal now, the governance canister stores in the registry that subnet A should hold the key with this identifier. And then subnet A's replicas will see, it should hold this key, but they don't hold it yet, and then they generate it. So that's now shown here on the right. Then they generate the key shares using distributed key generation, and then subnet A holds a freshly generated ECDSA key, a threshold ECDSA key. So that was now the first step. If we go ahead, we need another step. So as I said before, we want the key on at least 2 subnets. So how does this work? So we can do a so-called resharing of the key, which means we cryptographically reshare the key from subnet A to subnet B, of course, without ever reconstructing it. So this is a 2-phase cryptographic protocol. Again, it works in a way that in the first step, the first phase of the cryptographic protocol leads to the generation of so-called D-links, which are encrypted for the replicas of subnet B. And once subnet B is created with the proposal, subnet B will pull the information, so these D-links from the registry, and execute the second phase of this cryptographic protocol, and then have the key shared, secret shared analogously to A, of course, with different sharings. So that was now the second part, the resharing of the key. That's the more complicated one. And now the third proposal is easy. So once we want to, of course, use the keys for signing. So for this, we need to do one more explicit step, namely enabling one of the subnets or both if we wanted to, but we want to do it only for one. So enabling the subnet to respond to ECDSA signing requests. And once this is done, other canisters, so user canisters on any app subnet can make these crossnet requests for retrieving their public key or requesting signatures with a certain derivation path with the private key. And these are now the 3 phases summarized briefly. And now let's talk a bit more about how we want to deploy this in practice. So we want to have 2 phases. First one on the left side here, we want to have a beta release. So the beta release is due, let's say, early June. Let's be optimistic for that. So we're very far in the implementation. Early June might be realistic, first half of June. maybe within 2 weeks. This beta release is defined by generating a threshold ECDSA key, which will be clearly marked as a test key, like shown here, SEC-P256K1 test key. And the idea is that this is running or is being generated on a small subnet, like 13 nodes, because security is not so important. And we will delete this key at some point. So it's absolutely crucial that people do not use this key to secure any value, like on Bitcoin mainnet. The idea is really that this be used for working with Bitcoin testnet or other stuff for while developing and while testing your dApps. So once this is up, you can start implementing against this real interface. And here in red, it's really shown again, the test key will be deleted after testing at some point. Do not attach any value to this key. Now, the right side is what we will do for production. So during the beta phase, we expect that we will need to do some more things like performance tweaking. We are still up for code reviews, security reviews. So we have some small things to do still before we think this is production ready. And once we think it's production ready, we will do the production rollout process as shown before to receive, to obtain a state where we have the same key secret shared on 2 subnets, and one of the subnets will be the NNS, and one of the other subnets will be similarly sized, like 34 node roughly subnet that will be freshly created. And we will initially create the key on the NNS subnet, use the NNS subnet as the key backup subnet, and then reshare the key to the new subnet on the bottom, and then enable the subnet on the bottom to accept signing requests. And the NNS will not accept signing requests, but will be used only as a key backup subnet if something goes wrong in case of a disaster with the other subnet. So that was the introduction from my side and a brief overview. And now I'd like to hand over to Andrea, and he will give you some more details or many more details on how things work. So Andrea, the floor is yours.
Thanks a lot, Dieter. So yeah, I will try to give a bit more details about what Dieter just discussed. So before diving into the details of the 3 protocols or 3 steps that Dieter highlighted, I just wanted to give like a very high level introduction to interactive DKG and highlight a little bit what are the difference with the existing NI DKG that we already have integrated in the internet computer. So the interactive a distributed key generation protocol, to begin with, is just a protocol between 2 sets of parties, dealers and receivers, that are jointly trying to compute a common public key, which is associated to some secret key shares that are individual to the receivers. The way the protocol generally works at an high level is that the dealers contributes with some dealings, and these dealings contain some encrypted shares for the receivers. And these dealings are then combined together to compute, a common public key, and to compute also individual secret key shares for the receiver that can then use these secret key shares, for example, for signing operations. So in the case of non-interactive DKG, the protocol, at least from a level of flow, it's actually simpler, because these dealings that are computed by the dealers are publicly verifiable, meaning that if you get a dealing and you publicly verify, then you have the guarantee that the receiver will be able to decrypt their own shares, and that these shares will be correct. So you only need to see dealings, but you can publicly verify them, and you know that they are good to be used. The only thing that you need to be careful on is that you need to collect sufficiently many dealings to make sure that the secret they are sharing contains sufficient entropy. In the case of non-interactive DKG, things are, at least from a protocol perspective and in terms of flow, they're a bit more intricate. The main difference is that dealings are not publicly verifiable, or at least they're not entirely publicly verifiable. There are some parts that can be publicly verified, and indeed are, but there are certain parts that can only be verified directly by the receivers individually. And the way this works is that the receiver, they will get the dealings, there will be one ciphertext that is associated with them, and what they will do is that they will try to decrypt it and check whether the content of the secret key share they received is actually correct or not. In this way, receiver can privately verify whether the dealings make sense or not. However, in NADKG is simpler because since everybody can publicly verify, we really need to just collect sufficiently many dealings. For receiver, we want to decide which dealings to collect, but we want to make sure that the dealings we are using are actually make sense. So the way this works in interactive DKG is that the receivers, they will essentially show supports on dealings. And the way this works cryptographically is that when a receiver receives a dealings and verifies it, what it will do is that it will compute a multi-signatures on the dealings. And the idea is that we will try to collect to only use dealings that receive sufficient support from many receivers. Specifically, they will receive at least 2f+1 support from the receivers. So once we have sufficiently many dealings that have supports from the receivers, then we can combine them into a transcript. So this is quite a different approach than we have on non-interactive DKG. There's also another crucial step that is actually quite different, which is, for example, it could happen that that we include some dealings in the transcript that certain receiver may not be able to decrypt. So this dealing for a given receiver may contain just garbage and cannot decrypts to a wrong value that is not the correct shares that the receiver was supposed to receive. So interactive DKG deals explicitly with this situation and essentially enables receivers to have a mechanism to complain. So there's like a complaint proof that can generate, and this complaint proof essentially shows that indeed they receive like the wrong value in the ciphertext, and this will be used also. It would be sent to the other receivers, and the receiver will then help the receiver that got the wrong dealing to reconstruct his own secret shares. So once the receivers get his own secret shares, then we will be able to reconstruct his secret share for the common public key, and then we'll be able to use the key, for example, for signing. And so this was a very brief introduction on IDKGs, just to give a high-level overview of how the interactive DKG works and the crucial steps that are different with respect to non-interactive DKG. So now we can actually move back to what Dieter presented. So the three steps which we plan to use to roll out essentially the ECDSA feature to mainnet. So as Dieter mentioned, the first step is about generating a new threshold ECDSA key on the internet computer, and specifically on an existing subnet. So we have already many subnets on the internet computer. So we want to generate a new key that is used by one of the subnets. And specifically, we'll use this step to generate the keys on the DNS, and the DNS subnet will be used as a backup subnet for the threshold ECDSA key. So as Dieter already mentioned, this is initiated by a proposal. Specifically, this is going to be an update subnet proposal, and this type of proposal, what they do, they update the content of the subnet records on the registry. So just as a reminder, the registry is a key value store. It contains all information that is necessary to operate the internet computer protocol, and specifically the subnet records contain all parameters that are used by the subnet to operate. Among other things, they include, for example, the list of nodes that compose the subnet, the replica version, and from now on, or since recently, the subnet records can also contain a list of ECDSA key IDs that the subnet may hold. So going back to the proposal, this protocol will be initiated by a request to add a new key identifier to a given subnet. So this looks like exactly like any other proposal. So as usual, neurons will vote on it, and if this proposal passes, so if it's approved, when it's executed, the only thing that it will do is that it will update the subnet records to include this new key ID on the subnet. As usual, whenever there's a registry change, also the registry version gets increased, so also this will be increased as usual. So what happens after that? So after that, the subnet, we use this mechanism to update the subnet record to essentially signal the subnet that they should hold, this new key, which is called, in this case, SecP256K1 key 1. And so what the subnet does is that it periodically fetches, the most recent version of the registry, so the most recent changes that were published to the registry. And whenever it detects that, okay, from now on, it actually needs to hold a new copy of the key, they will check internally, okay, do I have a transcript for this key, for this threshold ECDSA key? If it doesn't have one, since we just introduced this key into the subnet record, what they will do is that they will initiate an IDKG protocol between the nodes of the subnet to generate this new key. So one crucial aspect of this is that so this IDKG protocol is really works like as I sketched before. The crucial thing is that both dealers and receivers are within the same subnet. So both the dealers that generate the dealings, the support shares, the complaint phase, all happens within a subnet. So they only need to exchange messages between themselves. So once this protocol is terminated, the subnet will end up with a new key transcript that will be included in the next catch-up package. However, this key is not propagated to the registry. So until now, this key is only present into the locally to the subnet. Okay, so this was really for the first protocol. So for the first step to generate, which led us to generate essentially a new threshold ECDSA key on the subnet. And specifically, just to remark that for the production release, we really aim to have this happening on the NNS subnet because it's the largest one we have available and is the one that is within more secure. So yeah, so this protocol will be used to have the key there and to be stored on the NNS subnet. So in the next, the second step mentioned by Dieter was about creating a new subnet and together with the possibility of resharing an existing key to this new subnet. Again, this process is initiated by a proposal. This time is initiated by, again, an existing proposal, which is a create subnet proposal. Unsurprisingly, this is used to create a new subnet, and this needs to include all sorts of parameters that are used by the subnet, including the list of nodes that needs to be assigned to it. So this needs to be unassigned nodes that are not already assigned to other subnets. And optionally, from now on, it will also be possible to specify a key identifier for a key for a ECDSA key that we would like this subnet to have. So this is again just another proposal. So as usual, this can be voted on by the neurons, and if this is accepted, then this request to create a new subnet is forwarded to the registry to be executed. So what usually happens when you create a new subnet is that the registry will try to create a new subnet record for this subnet. And before it can do that, it generally needs to create some key material for the subnet so that it can operate. And specifically, it needs to create some threshold BLS keys that are used, for example, for the random beacon or for certification. And these keys are usually generated, well, not usually, they are always generated by NNS subnet itself. So the registry, what it usually does is it makes a request to the NNS subnet to please create new NIDKG transcript so that I can give them to this new subnet. And the process for creating a subnet with an ECDSA key is very similar. So we want to have this subnet not only to have like NIDKG keys, so threshold BLS keys, but also to have like an ECDSA key. However, this key may, in general, not be hosted by NNS. This protocol generalizes also if keys are hosted on other subnets. But what the registry will do is then it will go see where this key is hosted, so which subnet holds this key. So in this case, for example, subnet A, and then make a request to subnet A's to please reshare the key that they hold to a certain list of nodes that will compose a new subnet. And this protocol, as we specify here in the slide, only mention a single key because for the initial deployment, that's all we envision, to have a single ECDSA key on the system. However, the protocol generalizes to multiple keys. So if one day we have multiple keys on the subnet, potentially keys for that are used for signing over different curves, then this protocol can be used to actually initialize a new subnet with multiple keys that may originate from different subnets. So once the registry issues the request to subnet A, what will happen is that the subnet A will initiate an IDKG protocol, so an interactive distributed key generation protocol. However, this is a special kind, meaning that this is like a crossnet resharing protocol. What this means is that the subnet A is trying to reshare its own key to nodes that lives on another subnet. And so essentially, if you recall the previous protocol, the previous description of the IDKG protocol, essentially here we split the participant to the subnet. Essentially, the dealers of the subnet live on subnet A, while the receiver of the subnet will live on a different one. What does it mean? This in terms of the protocol flow is that subnet A is only in charge to generate some D-links, and that's all the subnet A will do. However, all the rest of the protocol, the interactive protocol, will then happen on the newly created subnet. So all the collection of the multi-signature support from nodes, the creation of the transcript, the complaint phase, that will all happen on the newly created subnet. So once the subnet A initiate the protocol, what they will do, they will create some initial ECDSA D-links that are then returned to the registry. And what the registry will do finally to execute the subnet creation proposal will be to create a new subnet record for the new subnet, which with all the parameters that were specified in the proposal. Plus, it will also include in the initial subnet cap of the catch-up package of the new subnet, also this set of initial D-links that it received from subnet A. What happens is that, okay, subnet A, the nodes in subnet, nodes in subnet B will eventually realize that they are assigned to a subnet. Specifically, they will see that there's a registry version that contains a subnet record, and they are listed in the members of the subnet. So nodes will realize that they are assigned to a subnet. They will start running the Internet Computer Protocol among themselves. And specifically, they will see that in the catch-up package that they received from the registry, there's also a set of initial D-links there's also a set of initial D-links for keys like P256K1 underscore K1. What this means is that once the subnet started, they will try to finalize the cross-net resharing IDKG protocol that was initiated on subnet A. And what it means, again, they will perform they will try to collect sufficient support on the D-links that were generated on the other subnet. They will create a transcript, and then they eventually they will use this transcript. And if there are issues with some of the D-links, they will also handle the complaints among themselves. Of course, there are technicalities that distinguish the two protocols, but to an high level, the main caveat in order to be able to run this crossnet IDKG protocol is that the subnet A needs to collect sufficiently more D-links so that subnet B will be guaranteed to be able to terminate the protocol on the RAM, so that there's no interaction at this point needed between nodes of subnet A and subnet B. So all the interaction only happens locally to subnet B, essentially. Okay, so this was step 2. So with this step 2, essentially, we took an existing key that was already present on the internet computer, and we reshared this to another subnet. And this will really be the mechanism that we will use to essentially reshare the key that is backed up on DNS into a subnet that we deem secure enough to be used for ECDSA. And there's still one part that is missing. So at this point, we have key material on the internet computer. However, we still do not have signing enabled on the internet computer. So, one way to achieve that would be to any subnet that holds this key could answer this request. However, if you want to have a backup for the subnet, maybe we want to shield this subnet a bit more, so we don't want signing a request to the subnet. So we instead of relying on what's already on the subnet record, we essentially extended the registry to also include an explicit list of subnets that are allowed to sign with a specific ID. So this is the signing subnet list, which exactly as I said, it just keeps the mapping between which key identifier and which subnet is authorized to handle signing requests for this. Again, this is like a process that is initiated by a proposal. And once again, this is part of the update subnet proposal. And in this proposal, you can specify essentially that you want to have a subnet to be able to ECDSA sign, so to be enabled to sign with respect to a specific key identifier. As usual, this gets voted on, and if approved, upon execution of the proposal, the signing subnet list is updated, keeping a key identifier and mapping the key identifier to a subnet. So for the time being, we envision to only have a single subnet to handle signing requests. However, I mean, if this feature becomes very popular and is used a lot, it's not hard to envision that maybe this could be also extended to maybe list multiple subnets that hold a copy of the key to be able to handle answer a signing request. Okay, so these are the 3 steps and 3 protocols that Dieter mentioned earlier. So once we are able to run all these 3 steps, we will be in a situation where we have 2 subnets holding the key, 1 subnet that is enabled to answer a signing request. So maybe as a last thing for this presentation, maybe let's have a quick look of how the flow from Canister will really work behind the scene. So we have 2 main APIs related to ECDSA that were introduced in the system API recently. And these are 2 APIs, one for issue signing request. So Canister can call this API to request signature on an hash of a message using a specific derivation path and a specific key identifier. And the other API is for the Canister to be able to get public key. This could be either their own public key or could be somebody else's public key. And this, also as Dieter mentioned, also now allows for key derivation. We generally support a BIP32 derivation. Actually, we support something that is slightly stronger, so slightly more generalized. So there is a generalized BIP32 derivation, which is compatible with non-hardware BIP32 key derivation. So yeah, there are these 2 APIs that Canister can call. Any Canister on any application subnet can call these APIs. And once these calls are, once these calls reach the execution layer, essentially the execution layer, what it will do is that it will go to the registry and see, okay, which signing subnet is enabled for this specific key ID. It will identify which subnet it's actually used, can answer this request, and then this will be these calls will be forwarded to subnet the subnet that is enabled, and via crossnet messaging. So once these requests hit the subnet, well, there are a couple of things happening. So if it's a signing request, what will happen is that actually the nodes of that subnet are running another protocol, which is the threshold ECDSA protocol, to be able to compute the signatures on the given message. So this protocol is essentially an extension of the IDKG protocol. It requires several instances of IDKG happening. However, the protocol is structured in such a way that most of the computation can happen beforehand. So even before the message reaches the subnet. So subnet can do actually pre-computation, store key material, IDKG transcript essentially, that will be used during the signing phase. And then once the request for signing comes to the subnet, the nodes can non-interactively compute their signature shares that can be then aggregated to construct the ECDSA signatures. So this is for the signature case. Well, for the public key case, actually, this is much simpler. We don't actually need like a protocol to be able to answer this request. But essentially, given the main public key of the subnet, this can be used together with the Canister ID and the derivation path. This can be used to derive any key of the Canister. So as I said, this uses a generalized BIP32 key derivation scheme, which essentially includes the Canister ID in the path that is used to derive the Canister keys. Right. So when the subnet B receives this request, it handles them in this way, and then they can return the value to the application subnet that originates this request, which will then forward, which will then return the result by the system API to the canister that requested them. So this was really the main presentation that we wanted to, things that we wanted to discuss. So yeah, we are happy to take a question now, if there are any.
Yes, so Emma has collected the questions and I can read them to you now. So first question by Thomas. He's wondering whether the canisters itself will store any kind of derivable key. If not, will canisters be able to request some kind of key derivation to the subnet? So I think it might be good to explain the key derivation of canister level and beyond canister level in a bit more detail to make this clear.
Right. So, okay. So maybe let me try to answer first what I think is the question, then I can give a bit details of common context about the key derivation. So, so canister can decide, I mean, they have an API to request public keys, also their own public keys. And I mean, it's totally up to the canister to decide whether they want to store them or not. If they don't want to store them, they can, you know, just use the API to fetch them on demand. So going back to the comment that Dieter gave, yeah, maybe it's probably better to describe how the key derivation works. So key derivation really works as like a standard BIP32. So we start from a public key. So this is the subnet public key, and from the subnet public key, we derive essentially one master public key per canister. So this can be derived using a generalized BIP32. So in BIP32 derivation, essentially you can define an hierarchy of public keys that derive from your master public key. And usually the way you derive, at least how you derive the non-ardent keys, is that you specify a list of U32 integers that are used to derive like all the internal keys. So essentially, what BIP32 does is that it uses HMAC to hash the integer that is provided as part of the derivation path to generate the next key. And if you provide a list of these U32, you can derive like essentially a tree of subkeys. And we use a similar structure here. The only difference that we do is that we don't restrict BIP32 to just use integers, but we generalize BIP32 to use arbitrary long string. So, and we use this specifically in the derivation of the canister key. So each canister key is derived from the subnet key by using essentially the canister ID as a node in the derivation path. Given the canister master key, then one can do arbitrary derivation starting from there. And specifically, we can one can, if one wants to, you can just restrict to BIP32. So from the canister master key, from that point on, then they can do arbitrary derivation, either using the generalized BIP32 scheme or just the standard BIP32.
Okay, thanks, Andrea, for answering the question. I think this was lots of great detail and should have answered the question. There's more questions, so I think we have time for all of them. Next question by Marcos. Does the subnet A host user canisters?
So I guess this was referring to probably the initial diagram. So in this case, no. So subnet, so the idea is that both subnet that holds this key won't host user canister. This is specifically for the production deployment, where we plan to have the subnet A will essentially be an NS subnet, so there are no user canister installed there, and also the signing subnet, which will be subnet B, also that one won't host any user canister.
Thanks, Andrea. So maybe some more background why this is the case. So there's two reasons. One is user canisters would interfere in terms of compute resources. So this would require much more testing to get this reliably running. And the other reason is security. So even though we have currently implemented a sandboxing for canisters, so WASM execution is sandboxed into a separate process with a minimal surface integrating with the main replica process. We still think it's better to reduce the risk by not running any user canisters. So both security and resources are the two reasons for that. Next question is by Jordan. In your opinion, what are the most promising options for increasing the security of subnets? In particular, how many consensus nodes do you think a subnet will be able to handle in the near future? So if I may, I take this question. So there's multiple different paths how we can increase the security of the subnets. I mean, that's an extremely important point because the more value we have on the subnets, the more secure they need to be. So one option is to have more nodes. So more nodes means more people to be, or more parties that need to be compromised in order to run away with the value hosted on the subnet. Then another thing is that the decentralization, so the algorithm by which the nodes are selected from the different node providers, the different data centers, the different geographies, should be done in a way that decentralization is as good as it can be. So it means onboarding more node providers, onboarding more geographies, more different data centers. So all of this will help decentralization and also grow the number of nodes beyond 34 or 40, maybe to something much larger. But also it needs to be clear that the more nodes we have, the more it will lead to a graceful degradation of the performance of the subnet, because the more nodes we have, the longer it will take until we have consensus in a round. So round times will go up to maybe 2 seconds or 3 seconds if we increase the number of nodes more. So another approach that's very promising, or maybe promising, is to use AMD, SCV, SNP mechanisms for securing the VM that runs the replica. So this would mean that all the memory pages that go into the RAM out of the CPU would be encrypted. So it would be much, much harder to tap into the memory for a node provider. So you would need to do either some form of side channel attack or physically rig the machine in order to make such an attack. So this would raise the bar a lot. And there is plans, so there's currently some thinking doing that. Currently, we are enabling this technology only for boundary nodes in the first stage, but nothing speaks against also thinking of enabling this for the nodes themselves in the future. Next, another thing we could do is to have more stringent legal agreements with node providers, which means criminalizing actions of node providers, for example, like reading out the memory of machines. Of course, it's still hard to prove, but it again raises the bar. Another thing might be node rotation, so meaning to rotate out and rotate in nodes of subnets randomly, unpredictably at random times, so that it's harder to form an attack coalition that could compromise the key. And we think all of those, or a subset of those mechanisms, will lead to sufficiently good security in order to run threshold ECDSA with large value protected by the key on the internet computer. So next question for Andrea by Tuong. How many times can an ECDSA key be reshared?
There's really no limit to how many times it can be reshared. So as many proposals to reshare possible.
Good, thanks. That was short and crisp. Next question by Jordan again. How long will an ECDSA signing request take to complete? Do you have any numbers or throughput per ECDSA subnet, like in the sense of signing requests per unit time?
I think we don't have like very good numbers, or at least to share. I think one thing to mention is that we really want to do this beta release really for testing out things, and especially in terms of performance. I would say that at the moment, there are still a lot of optimization that can be done. So I think initially, maybe the efficiency will not be super performant, but I'm expecting that we will be able to improve the performance significantly in the next releases.
Thanks, Andrea. So maybe to add something. So maybe to add something on top. So the protocol itself is designed that the large part of the computation is done in a pre-computing stage, as Victor explained last year, like for this pre-computing those quadruples, and then the actual signature is the lesser part of the effort, but still overall everything is quite computationally intense. And as Andrea said, we will see how long it takes. Next question by Jerome. Just a reminder, when is the beta version expected and production? So I'll take this one. So rough estimate, no firm commitment. Beta might be out in 2 weeks. I would say at the latest by end of the first half of June. So mid-June, we should definitely have it out. And production sometime July. Next question, will we be able to sign Ethereum transactions as soon as this reaches production, or are there upgrades needed to the ECDSA signing protocol? So yeah, this is possible, and I think Ben Lin already made an implementation or is making implementation as a showcase to sign Ethereum transactions. So it doesn't need an update. Next question for Andrea would be, how hard will ECDSA support be to implement? Is that on the roadmap?
So at the moment, I think it's not concretely on the roadmap or on the short term. I think ECDSA, I mean, Schnorr signatures are generally easier to handle. So I think ECDSA, threshold ECDSA is actually a bit more complicated. I think ECDSA, may end up, being easier to implement. Yeah, so this is not concrete on the roadmap, but I would also assume that that many of the things that we are actually doing for ECDSA could be recycled for ECDSA and or Schnorr signatures. So I would hope that generalizing to another signature scheme like Schnorr, I think it should be definitely simpler than what we did now for ECDSA.
Thanks, Andrea. And then there's the next question for you. So by Tomasz again. So he thanks you for the explanation, and he's got another question. Is there a limit to how many keys a canister can request from the subnet?
Sorry, can you repeat the question?
Yeah, is there a limit to how many keys a canister can request from the subnet? I think he means how many keys can be derived using the BIP32 mechanism. I think.
Yeah, so I mean, yeah, there's no so hard limit, right? So you can have arbitrary derivation paths, so you can derive essentially as many as you want. And if the question was about how many requests the canister can make, I don't think we have like hard limit on that. So I think the canister can still request as many as they want.
Yeah, I guess for the mathematicians among you, it's countably infinitely many keys that each canister can have. And the next one, so any canister deploy on the ECDSA signing subnet list are allowed to sign using this key. Okay, I need to reread that.
I think so. It's not only so we plan not to have any canister on the subnet that is enabled to sign, but once we have at least one subnet that is listed there, any canister on the IC can actually is enabled to make a ECDSA signing request.
Okay, thanks. So the next question by Brian. If the hardware is known and if it's running open source firmware, what concerns would there be in using ECDSA? The concern is that people might invest heavily against this tech. So Andrea, do you want to take a stab at it?
Sorry, can you repeat the question?
Yeah. So if the hardware is known and if it is running open source firmware, what concerns would there be in using ECDSA? The concern is that people might invest heavily against this tech. So I really don't understand it. So Brian, could you maybe reformulate it in the chat and we ask it later? I'll go on meanwhile. So Marcos has again a question. How easy will it be to use this ECDSA feature for other blockchain integrations? Can community do it?
I mean, sure. Like, I mean, the basic signing functionality can be used for anything, right? Even beyond integrating with other subnets. So I think this enables, really the community to integrate with many other projects.
Yes. So specifically, for example, if the community wanted to, you could just build an integration with another blockchain that signs transaction with ECDSA, and use a relay-based architecture for relaying blocks into the IC and relaying transactions out. So anybody could build this right away. So it's pretty powerful. You just use this interface and use relays to get blocks and transactions in and out, and you could integrate with essentially any other blockchain you want to. Next question. By Brian, how do you actually know that the ECDSA is running the open source firmware and not the modified version installed by the manufacturer or replaced in transit?
I'm not sure what he means by that.
So I think he refers to the correctness of the code. So I guess this is handled by getting the proper build hash approved by the NNS and people voting for it and people looking at it. So I think that's the mechanism to ensure that things run properly. And in the future, we could have even at the station using AMD, SCV, SNB, which means anybody could get an attestation, or the NNS subnet could get an attestation from each ECDSA node that they are running the correct thing. I mean, it's an important question, but I think the basic answer is thanks to the voting mechanism of the NNS that anybody can look at the code that's being deployed, and then the build has a specific hash, and this is getting voted on, and this is getting deployed, guaranteed by the NNS. This ensures that the right thing is running. Next. So Jordan is making a comment that with ECDSA and EDDSA, we could sign transactions for most blockchains. Yes, so Jordan emphasizes that EDDSA would be pretty cool to have. Agreed, yeah, so we should maybe look at it at some point. So Schnorr has been discussed a little bit. It's easier, as Andrea said, but yeah, something to be discussed some other time. Next question by Jerome. To follow up on Jordan's question regarding Ethereum transactions. How Ethereum or Bitcoin focused is this? Support for Solana, Polkadot, etc. Is this possible? So essentially everything that uses ECDSA would be possible to support in terms of integrations. Right, Jordan responded to this in the chat already. So Thomas has another question. Is there any plans of adding support for other curves like ED 25519? Andrea, want to take this one?
Yeah, so I guess ED 25519 is just the EDDSA, right? So,
okay, yeah. Good. Okay. I think we ran out of questions. Let me just quickly check. So there's one that I think that was reformulated. Yeah, I think we are through all the questions. If there's nothing else, I think I would like to thank everybody for attending. I hope you could take something away. Thanks for listening in and hope to see you soon again. Goodbye, everybody.